Hello, and welcome to this presentation related to the solution of second-order differential equations of the form d2y by dx squared is equal to a function of x. Here's an overview of the presentation. We commence with some reference information. We state underpinning knowledge required, show extracts of tables related to integration of standard forms, the laws and the rules of indices. And we have an introduction related to the solution of the differential equations having the form d2y by dx squared equals to a function of x. And within the introduction we will outline the generic solution process, essentially integrating twice to form either a general solution or a particular solution. Then we have a series of examples. Example 1 solves the differential equation 4 multiplied by d2y by dx squared is equal to a polynomial function of 12x minus 8. We show the general solution here. Next we have example 2, d2y by dt squared is equal to 2 multiplied by the sine t divided by 3, and again we form a general solution. And we have example 3, 2 multiplied by d2 beta by dx squared is equal to an exponential function, and we form in this case a particular solution. Then we have some questions. First batch of questions relate to differential equations of the form d2y by dx squared equals to ax plus b. That's a polynomial function. Then questions related to differential equations of the form d2y by dx squared is equal to sine ax or cos ax, or trigonometric functions. And then questions related to equations of the form d2y by dx squared is equal to ETAX, or exponential function. And we conclude the presentation with a few descriptive questions of the form d2y by dx squared is equal to a function of x. And here are the approximate start times related to the various sections contained within the presentation, hopefully to aid your ease of access through the presentation, but please note that generally all times are rounded to the nearest minute. Here's the start of the reference information. There is underpinning knowledge required here because of the solution sequence for the differential equations. We do need a strong understanding of integration using standard forms, and there are 2 lecture videos available that will help with this underpinning knowledge. The first is a live lecture related to integration using standard forms, and the second is a pre-recorded lecture which covers essentially the same information but perhaps in a more structured way. We strongly encourage you to review at least one of these presentations before reviewing the contents of this presentation. Reference information continued. Here's an extract from table 1 of our previous presentations related to the table of standard integrals. These are just extracts here showing the 4 main types of integral we'll be considering within the various solutions presented. Reference information continued, and I've also included here the definition of a logarithm, laws of logarithms, and the laws and the rules of indices. For further reference, there are actually presentations related to the solution of first order differential equations, which again does provide background information, although not essential to understanding the solutions we're going to present in this presentation. There are actually 4 types of first order differential equation that are considered. A brief introduction to the solution of second order differential equations. The generic form of the typical second order differential equation is as shown below. Constant a multiplied by d2y by dx squared plus b multiplied by dy by dx plus c multiplied by y is equal to a function of x. Within this presentation, the equations have a simplified form, as shown below. d2y by dx squared is equal to a function of x. If you want to see solutions to the generic form, shown here, there are separate presentations related to the solution of the second order differential equations. But let's now consider the solution process for the simplified form of the second order differential equation. So the solution sequence for the simplified equations is outlined below. Step 1, we will integrate the given second order differential equation in this format to find dy by dx. If there are values stated in the question for x and dy by dx, we will then find the constant of integration, C1. Step 2, we integrate a second time, this time to find y, and if values are stated for x and y, we will again find the constant of integration, C2. Step 3, we simply state the final equation in the form of either the general solution, that's when the solution contains unknown constants C1 and C2, or we state it in the particular solution, that's where we've been able to solve for the values of constants C1 and C2. They're known numerically. The questions dictate whether we determine the general solution or the particular solution. Let's now consider some examples related to this type of differential equation. So here's example 1. We're asked to find the general solution of the equation 4 multiplied by d2y by dx squared is equal to 12x minus 8. So here's the solution. So given the differential equation shown above, first thing we're going to do is rearrange the equation, in this case dividing both sides throughout by 4. So we have d2y by dx squared is equal to, and divide the 12 by 4, that becomes 3x. And the negative 8 divided by 4 becomes negative 2. And essentially we're ready for step 1. We're integrating for the first time. Left hand side becomes dy by dx. On the right hand side, using our standard forms, going back to this table here, using standard form 1, which is the polynomial here, ax to the n integrates to ax to the n plus 1 over n plus 1. And of course we must add the constant integration at the end of the integration process. So on the right hand side, 3x integrates to 3x to the 2 divided by 2, and minus 2 integrates to minus 2x. And there's our constant integration. I've called it C1 because we'll be integrating twice here. So there'll be 2 constants of integration. Second step, integrating the second time. Now we have on the left hand side y. Again, each integrates on the right hand side. 3x squared divided by 2 integrates to 3x to the cube divided by 6. 3 times 2 is 6 on the bottom line. Then minus 2x integrates to minus 2x squared divided by 2. Constant C1 will integrate to C1x. And we add our second constant integration because we've integrated the second time. Labelled that C2. In step 3, as the question stated to find the general solution, then that's what we state the final answer as. So on the left hand side, y is equal to, I just tidied up the previous line, 3 divided by 6 is a half, so a half x cubed, and 2 divided by 2 of course is 1 here, so it's minus x squared plus c1x plus c2. So there's our full solution to example 1, finding the general solution in this case of our differential equation of the form d2y by dx squared equals to a function of x. Example 2, has to find again the general solution of the equation d2x by dt squared is equal to 2 multiplied by the sine of t divided by 3. Notice the variables are changing here just to try and acclimatize you to the type of variables you might consider in various solutions, but it's still of the generic form d2y by dx squared equals to a function of x. So here's the solution. So given the differential equation above, d2x by dt squared equals to 2 sine t upon 3. Step 1, we integrate for the first time, so left hand side becomes in this case dx by dt. On the right hand side again, this is a standard form of sine ax, and again from our standard tables, sine ax integrates to negative cos ax divided by a plus the constant of integration c. So considering the sine, t divided by 3, that integrates to negative cos t divided by 3, or divided by a third. That's the value of a in this case. So it's negative 2 cos t upon 3 divided by 1/3. Just again, think that through for yourself. We've covered this type of integral in the previous presentation. So considering the generic form of sine ax, the a in this case would actually be 1/3. And of course we add the constant of integration, c1. On the next line I've just simplified this step 1 for dx by dt, because dividing by 1/3 is actually like multiplying by 3. So that's why I can write this now as -6 cos t divided by 3 plus my c1. Example 2 continued, and for reference here's an extract from our fractions video specifically relating to division of fractions, where we included the algebraic proof as shown below here. When we're dividing fraction a upon b by c upon d, it can be shown that that's the same as the fraction a upon b multiplied by d upon c. So in example 2 we're considering calculation of -2 multiplied by cos of t divided by 3, which is all divided by 1 upon 3, a third. So that's shown as one-line formatting. If we write that now on two-line formatting, this would be the numerator, the -2 multiplied by the cos of t upon 3, and our denominator is 1 upon 3, a third. If we now apply the a, b, c, d formatting, our -2 cos t upon 3 is a, and that's effectively divided by 1 in this case, so that's the b, and the 1 upon 3 is the c and the d respectively. So following the algebraic proof, we can now turn the division sum into multiplication sum by still having the a upon b on the top line. But notice we inverted the c upon d fraction. We now have d on the top line and c on the bottom line. So now we've turned our division sum into a multiplication sum. So our solution now will be 3 multiplied by -2, so it's -6 multiplied by the cos of t upon 3. So I've labelled the process on this slide just to try and show you how we're actually using division of fractions to simplify our expression. Second step, we now integrate again. So for a second time, and we get x on the left hand side, this time is equal to -6 multiplied by the sine of t divided by 3 again, divided by a third, because we're integrating again of course. And referring back to our standard tables, this shows cos ax when integrated becomes sine ax upon a plus c. Add my c1x, add my c2, second constant, and step 3, just tidying up for the final general solution. We get x is equal to, and again dividing by a third on the previous line is like multiplying by 3, so 3 times -6 is -18. So we get -18 multiplied by the sine of t divided by 3 plus c1x plus c2 as our final solution for example 2. Let's consider example 3. This is written as a descriptive problem, but the same solution sequence is required. So the context here, the temperature, beta, of water in a container when subject to external heat energy is simulated by the differential equation 2 multiplied by d2 beta by dx squared is equal to negative e to the power of -2x divided by 9. Just note the formatting I've used there for the exponential, often using spreadsheet software packages. We're asked to solve the equation for the particular solution this time, and we're given that when x is equal to 0, beta is equal to 2, and d beta by dx is equal to 3. The question then says, using the solution found, we've got to determine the temperature of the water when time x is equal to 5s. So in this case they're using the symbol x for time instead of t. So let's consider the solution of this second order differential equation. Again it's of the form d2y by dx squared equals to a function of x. Just note as it's given in the form of 2 multiplied by d2 beta by dx squared equals to negative e to the negative 2x upon 9. I'm just going to divide both sides by 2. So it's of the form d2 beta by dx squared, and that's equal to negative 0.5 e to the negative 2x divided by 9. So I just divided both sides by 2 essentially. Instead of using the fraction on the right hand side of a half, I've used decimal 0.5 here. So now we're ready to undertake the 3-step process. Example 3, solution continued. Just repeated this line from the previous slide for our convenience. So now step 1, we integrate for the first time. So on the left hand side we have d beta by dx is equal to negative 0.5 e to the power of negative 2x divided by 9, and that's all divided by negative 2 divided by 9. We refer back to our standard tables of integrals. E to the ax integrated becomes e to the ax divided by a plus our constant of integration. So note in this case our a is negative 2 divided by 9. So that's why we're dividing by negative 2 divided by 9. And of course we add our constant of integration c1. So next line we simplify the right hand side. So d beta by dx is equal to 2.25 multiplied by e to the negative 2x divided by 9 plus c1. Note to obtain the 2.25 here, that's negative 0.5 multiplied by 9 divided by negative 2. Again, we're back to our fraction format. Example 3 continued, and again purely for reference, this slide shows our division of fractions. We consider our one-line format in here. We got negative 0.5 multiplied by e to the negative 2x divided by 9, and that's all divided by negative 2 divided by 9. Referring to our algebraic proof of division of fractions, we can actually write that as 9 multiplied by the negative 0.5 multiplied by the exponential function divided by negative 2. And of course that evaluates then to 2.25 multiplied by the exponential function. And again, that's just for reference to show you how we manipulated the division of fractions in example 3. Next we impose the initial condition given in the question. That's when x is equal to 0, d beta by dx equal to 3. So on the left hand side of our equation we have 3. On the right hand side we place a 0 wherever we have an x. Evaluating, note e to the power of 0 is 1. So now we can see we can simply rearrange the equation for c1 by subtracting 2.25 from both sides of the equation. c1 is equal to 0.75. Now we have our equation for the first differential here, d beta by dx. That's equal to 2.25 multiplied by e to the negative 2x divided by 9 plus 0.75. Example 3, solution continued. Just repeated this equation from the previous slide for convenience. And now step 2, we integrate for the second time. So integrating again, we have beta on the left hand side is equal to 2.25 e to the negative 2x divided by 9. Again, it's divided by negative 2 upon 9 following our standard integral pattern plus 0.75x plus constant of integration c2. Simplifying for beta, we have negative 10.125 e to the negative 2x divided by 9 plus 0.75 plus c2. Again, notice that the negative 10.125 is calculated from 2.25 multiplied by 9 divided by negative 2. Again, using our division of fractions procedure. Imposing the initial condition given in the question that when x is 0, beta is equal to 2. So this time we have 2 on the left hand side, and wherever we have an x on the right hand side, we replace that with a 0. So again, notice on the next line that the e to the 0 is 1 again, and we can clearly see we can rearrange by adding 10.125 to both sides of the equation. So c2 is 12.125. So step 3, we can now state the particular solution for beta. It's negative 10.125 e to the negative 2x divided by 9 plus 0.75x plus the 12.125. What I've done on the final line is rearrange the terms so I have a positive value to begin with, so positive 12.125x, then I plus my 0.75x, and then minus the 10.125 e to the negative 2x divided by 9. So example 3, solution continued. Just repeated the equation for beta from the previous slide. Now we have to find the temperature, it's beta of course, when x is equal to 5. So all I now do is put the value of 5 in the above equation, or when I see an x, so it's 12.125 plus 0.75 multiplied by x, that's a 5 there, and then we minus the 10.125 multiplied by e to the negative 2x, which is 5, divided by 9. I'll let you do the evaluation. You should find that beta is equal to 12.5 degrees. That's the temperature of the water being heated after 5 seconds has elapsed. That's the solution to example 3. On the following slide, I've just shown some reference information. So example 3, solution continued. This is purely for reference. On this slide, I've shown the solution for this second order differential equation plotted. So this is the curve for beta, plotted on a graph, showing temperature in degrees C against time in seconds. The graph clearly shows that when x is equal to 0, beta is equal to 2. A scale there of 0 to 5. And also when x is equal to 5 seconds here, we can see that the beta value is 12.5 degrees. It reads off as 12.5 degrees here on our scale. Example 3, solution continued. And again, this is purely for reference. I've shown various coordinates in the table, commencing from time is equal to 0 to 20 seconds, and the appropriate beta value is being calculated. Also stated a few characteristics of the graph itself, but we will not be plotting the graphs and describing the curves in the rest of the presentation. Let's now consider some second order differential equations of the form d2y by dx squared equals to a function of x, which involve polynomial functions. So question 1a is 2 multiplied by d2y by dx squared is equal to x plus 6. And question 2a, d2s by dt squared is equal to 9t squared minus 5. We're given some parameters here of t is equal to 0, s is equal to 0, and ds by dt is equal to 1. Note for reference, the answers are given in these square brackets. I would encourage you to stop the presentation and attempt questions 1a and 2a, but the full work solutions to both questions will be shown on the following slide. So here's the solution to question 1a. The question is stated in the form of 2 multiplied by d2y by dx squared equals x plus 6. But what we're going to do is rearrange the equation into the form of d2y by dx squared equals a function of x by simply dividing both sides by 2. So on the left hand side we have d2y by dx squared, and on the right hand side we simply divide the x by 2, so x upon 2, and the 6 by 2, so that's plus 3. So integrating for the first time to find dy by dx, that's equal to x to the 2 upon 4 plus 3x plus our constant of integration c1. No initial or boundary condition has been given this time, so we leave dy by dx with the c1 unknown, and then we integrate the second time to find y, and integrating x squared upon 4 becomes x cubed upon 12 from our standard form, plus 3x becomes plus 3x squared divided by 2, plus c1 becomes plus c1x, and then we add our second constant of integration. So that's the general solution to question 1a. Question 2a, commencement of the solution. We're given the differential equation d2s by dt squared is equal to 9t squared minus 5. Integrating for the first time, left hand side we have ds by dt, and notice on the right hand side these are all standard forms. Here's our table of standard integrals showing the ax to the n function. So integrating 9t squared with respect to t becomes 9t cubed upon 3, and minus 5 integrates to minus 5t, and we add our constant of integration c1. Simplifying on the next line, ds by dt is equal to 3t cubed minus 5t plus c1. Notice that the 9 divided by 3 equals 3, shown here. And inserting our initial condition, given in the question that t is equal to 0, ds by dt is equal to 1. So 1 on the left hand side, and then we replace the t on the right hand side with the 0, shown here and here. We can clearly see C1 evaluates to 1, so ds by dt can be written as 3t cubed minus 5t plus 1. Question 2a, solution continued. Just repeated this line from the previous slide for convenience. Now integrating the second time, left hand side we now have s, and again integrating with our standard forms ax to the n, we now have 3t to the 4 divided by 4 minus 5t squared divided by 2 plus 1t plus constant integration c2. Inserting the initial condition given in the question, this time t is equal to 0, s is equal to 0. We now have 0 on the left hand side, and replace a 0 wherever we see, and t on the right hand side, so here, here and here, my equation. By inspection we can see that c2 is 0. So our final solution for s is 3t to the power 4 divided by 4 minus 5t squared divided by 2 plus t. And that's the full solution to question 2a. Here are some tutorial questions involving sinusoidal functions. Again, they're all of the form d2y divided by dx squared equals the function of x. As I said, the functions now are sinusoidal. So question 1b, d2y by dt squared is equal to sine of t. And question 2b, for third, multiplied by d2y by dx squared, that's equal to sine of 2x. Again, on the right hand side in the square brackets are the solutions to each of the questions. Again, I'd encourage you to stop the presentation and attempt question 1b and 2b, but the full solution for question 1b is shown on the following slide. So question 1b, here's the solution. So we're given d2y by dt squared is equal to sine of t. So integrating dy by dt is equal to negative cos t plus our constant integration c1. And here's our solution for integrating sine ax becomes negative cos ax upon a, and of course the a in this case is 1. Don't write the ones, but they're there, it's 1t. And integrating again, we have y is equal to negative sine t plus c1t plus c2. So that's the general solution for question 1b. And here are some second order differential equation questions involving sinusoidal functions, but this time we have to find the particular solutions. You can develop your solutions to these questions at your own pace. Again, the answers are shown in the square brackets on the right hand side. Note the full solution to question 3b is shown on the following slides. Here's the commencement of the solution to question 3b. Given the differential equation, d2y by dt squared is equal to negative 2 multiplied by the cos of 0.5t. Integrating for the first time, dy by dt is equal to negative 2 multiplied by the sine of 0.5t divided by 0.5 plus our c1. Again, noting dividing by 0.5 is like multiplying by 2. So on the next line we can simplify dy by dt is equal to negative 4 multiplied by the sine of 0.5t plus c1. Next we impose the initial condition given in the question. Time t is equal to 0, dy by dt is equal to 3. So in our equation, left hand side have 3, on the right hand side we put the 0 where we have a t, so in our bracket here. Note the sign of 0 is 0, so we can evaluate c1. c1 is 3. So now dy by dt is equal to negative 4 multiplied by the sine of 0.5t plus 3. Question 3b, solution continued. Just repeated this line from the previous slide for convenience. So integrating for the second time, y is now equal to -4 multiplied by negative cos of 0.5t divided by 0.5. That's the result of integrating sine of 0.5t above. And again, we're referring to the standard integral tables here. Plus 3t plus c2. Again, notice dividing by 0.5 is the same as multiplying by 2, and of course I have a double negative here. So simplifying on the next line, y is equal to positive 8 multiplied by the cos of 0.5t plus 3t plus c2. In the question, we're given that when t is equal to 0, y is equal to 5. So imposing the initial condition given, we have 5 on the left hand side of the equation, and we place a 0 wherever we have a t on the right hand side. Note that cos of 0 is actually 1. So essentially we have the equation 5 is equal to 8 plus c2. And subtracting 8 from both sides of the equation, we find c2 is equal to -3. Simplifying for y is equal to 8 multiplied by the cos of 0.5t plus 3t minus 3. What I've done on the final line is slightly rearrange the terms, just bringing the 3t term to the front of the expression, which is a convention for this particular problem to have the t in front of the cos t term. So that's the full solution for question 3b. Here are some second order differential equation questions involving the exponential functions. So they're of the form of d2y divided by dx squared equals a function of x, where the function of x is an exponential. For the first batch of questions, we're asked to find the general solutions. So question 1c, we're given d2y by dx squared is equal to -0.5 multiplied by e to the -0.2x. Question 2c, d2y by dx squared is equal to 1.2 multiplied by e to the power of 0.3x. Just notice a slight formatting change here for the exponential. Question 3c, d2y by dt squared is equal to negative e to the power of -t. Question 4c, a half multiplied by d2x by dt squared is equal to negative e to the -0.25t. And question 5c, d2y divided by dx squared is equal to ae to the -kx. The final solution to each of the questions is shown in the square brackets on the right hand side. I would encourage you to stop the presentation and attempt questions 1c to 5c, but I will show you the full work solution to question 1c on the following slide. Question 1c, it's the full solution. Given in the question, d2y by dx squared is equal to -0.5 multiplied by e to the power of -0.2x. So integrating, we have dy by dx is equal to -0.5 e to the -0.2x divided by -0.2. So our a value here is -0.2. And we add our constant integration c1. Simplifying the right hand side, we now have dy by dx is equal to 2.5 e to the -0.2x plus c1. Note the -0.5 divided by -0.2 evaluates to 2.5, shown here. And integrating again, we now have y is equal to 2.5 e to the -0.2x divided by -0.2 plus c1x plus c2. Simplifying, y is equal to -12.5. That's now the 2.5 divided by -0.2 e to the -0.2x plus c1x plus c2. So that's a general solution for question 1c. And here are some more second order differential equations related to solving problems where the function of x is an exponential. In questions 6c through to 10c, we have to find the particular solution. So we have a stated differential equation, and we're given parameters, or sometimes called the initial condition, associated with the equation. That will allow us to find the particular solutions. I'll let you review the questions at your own pace, but I would encourage you to start the presentation and attempt questions 6C through to 10C, noting that the final solution for each of the questions is stated in the square brackets at the right hand side. I will show you the full work solution to question 6 on the following slides. Question 6C, commencement of the solution. So we're given in the question d2y by dx squared is equal to 0.3 multiplied by e to the negative 0.4x. So integrating the first time, we have dy by dx is equal to 0.3 e to the negative 0.4x divided by negative 0.4, that's the a value here, plus c1. Simplifying the right hand side on the next line, dy by dx is equal to negative 0.75, that's the 0.3 divided by negative 0.4, multiplied by e to the negative 0.4x plus c1. Imposing the initial condition given in the question, x is equal to 0, dy by dx is equal to 0. So we have 0 on the left hand side, and on the right hand side we put the value of 0 where we have an x. Again, notice that e to the 0 will be 1 here, so we can clearly see that c1 is 0.75. So our equation for dy by dx is equal to negative 0.75 e to the negative 0.4x plus 0.75. Question 6C, solution continued. Just repeated this equation from the previous slide for convenience. So integrating for the second time, we now have y is equal to negative 0.75 e to the negative 0.4x divided by negative 0.4, so our standard integral, plus 0.75x plus c2. Simplifying, y is equal to the 1.875 multiplied by e to the negative 0.4x. The rest of the equation is the same as the previous line. Then imposing the initial condition given, this time when x is equal to 0, y is equal to 0. So on the left hand side we have 0, and replace the x on the right hand side with 0. So again, notice that e to the 0 is 1 here, and we can clearly see rearranging that c2 will be negative 1.875. So we can write y as 1.875 e to the negative 0.4x plus 0.7x minus 1.875. Or if you want to, we could factorize on the 1.875. It occurs twice in the line above. So I put 1.875 here, and inside the bracket we have e to the negative 0.4x minus 1, then plus the 0.75x. So an alternative format for the final solution. So that's the complete solution now for question 6C. Let's now consider a few descriptive questions. These require the same generic solution as all the previous questions. It's just that we're confronted with the differential equation now wrapped within a context. So here's question 1. The temperature theta of water in a barrel when subjected to heating from an element is modelled by the equation d2 theta by dt squared is equal to negative 0.5 e to the negative 2t divided by 7. We're asked to solve the equation given that t is equal to 1, theta is equal to 3, and d theta dt is equal to 2. Using the final solution, we need to determine the temperature of the water when time t is equal to 6 seconds. Here are the answers to the question for your reference. And I would now encourage you to start the presentation and attempt question 1, but I will show you the full work solution on the following slides. So here's question 1, commencement of the solution. So we're given from the question the equation d2 theta by dt squared is equal to negative 0.5 e to the negative 2t divided by 7. So integrating to find d theta by dt, That becomes negative 0.5 e to the negative 2t divided by 7. That's all divided by negative 2 upon 7. That's the a value in our exponential function. And of course we add the c1. Simplifying the right hand side of the equation, we now have d theta by dt is equal to 1.75 e to the negative 2t divided by 7 plus c1. And question 1, solution continued. Again, purely for reference, showing our division of fractions process, we have negative 0.5 multiplied by e to the negative 2t divided by 7, and we're dividing that by negative 2 divided by 7. The fractions process here shows how we end up with 1.75 multiplied by the e to the negative 2t upon 7. If we now impose the initial condition given in the question, when t is equal to 1, d theta by dt is equal to 2. We have 2 on the left hand side here, and 1 for the t value on the right hand side. We can evaluate constant c1 as 0.68491. So that now gives us d theta by dt, shown in this format here. And question 1, solution continued. Just repeated this line from the previous slide for convenience. So integrating the second time, theta is equal to 1.75 e to the negative 2t divided by 7, again all divided by negative 2 divided by 7, plus 0.68941t, plus the new constant c2. Simplifying on the next line, theta is equal to negative 6 1/8. That's found by 1.75 multiplied by 7 divided by negative 2. That's multiplied by e to the negative 2t divided by 7, plus the rest of the expression on the right hand side. And imposing the initial condition given, when t is equal to 1, theta is equal to 3. So 3 on the left hand side, put the value of 1 for t on the right hand side. We can evaluate c2 as 6.9179. So that now gives us our final solution. Theta is equal to this expression here, which has just been slightly rearranged on the following line to have a positive term in the front of the expression. And finally, we're asked to find the value of theta, the value of temperature, when time t is equal to 6 seconds. So I've labelled that theta 6 here. So just put the value of 6 where there's a t in the above solution. And evaluating the temperature at 6 seconds is 9.9 degrees C to 2 significant figures. So that's the full solution to descriptive question 1. Here's question 2 for your reference. I'll let you review this at your own pace. The solution is given in the square bracket here. And finally question 3. Again, I'll let you review this at your own pace, with solutions again in the square bracket. That concludes the presentation, which I hope has been of some use to you, and as always, thank you for viewing.